In this video, we're going to be talking a little bit about free fall. So free fall is really the perfect scenario where the only thing that is happening is our object is falling. Okay? And when our object is falling, there's a few things that we can assume. So in the idealized case of an object falling where air resistance is neglected, and that's important to remember that air resistance is not there. There is no air. Such motion is called free fall. And that's the type of motion that we're going to be talking about. Okay? In this case, the acceleration of the object is constant and equal to the free fall acceleration. And the free fall acceleration on Earth is denoted by the letter lowercase g and has a numerical value near the surface of the Earth of about 9.8 meters per second squared, or 32 feet per second squared, and is directed downward towards the center of the Earth. I'm going to write this over here. Downward towards the center of the Earth. Okay? And that's important to remember, so don't forget it. And whenever we're referring to a free-falling object, we're not necessarily referring to an object which has been dropped. That's a very common misconception, is that free fall means that something has to be dropped. Not necessarily, but we are referring to any object which is under only the influence of gravity. So under the influence of gravity only. It's very hard to write on this thing. Okay. When substituting the acceleration due to gravity in an equation for motion, the sign of the acceleration will depend on the coordinate system I choose. And what I mean by that is this. Right? If I have an object, a ball, and I'm dropping it from a table, maybe, okay, my coordinate system is dependent upon which direction I choose is positive and which direction I choose is negative. Most of the time, we choose up as positive and down is negative. So in this case, the sign for my acceleration due to gravity would be negative. Okay? Whenever I write the letter G, I mean that 9.8 meters per second squared is my acceleration, which means I'm defining my coordinate system as down is positive and up is negative. If I choose a coordinate system where up is positive, then I will write A is equal to negative G. Okay? And you should do the same, because that's important to remember. If we look at a graph of motion for a particle dropped that has an initial velocity of 0, we'll get the following position versus time graph on a velocity time graph. Well, if we're dropping it, and we say that our origin, or we say we're dropping it from this point, it's falling to the ground, it's falling downward, then that means that as time goes on, it's going to be speeding up. Okay? And velocity time, it's moving in the negative direction and speeding up. My velocity time graph would look like that. If I look at a graph for the motion of a particle thrown downward, now this is a little bit different because I'm throwing the ball downward with some initial velocity v naught, we'll get the following. Well, if I'm throwing it downward, that means that I have an initial velocity of v naught, and I'm still accelerating downward. Okay? On a position time graph, that means that I'm starting off with some velocity and going faster. If I look at a graph of motion for an object thrown upward with an initial velocity v naught, then that means I'm starting here, it's going up, and then it's going to slow down, and then it's going to come back down. Okay? If I do the same thing here, starting with an initial velocity v naught, I'm going up, I'm slowing down, and then I'm speeding up, moving in the negative direction. Okay? In this case, this maybe is my height, the highest point, and the time for an object to rise to a height h is the same as the time for an object to fall to the same height. So if I have an object here, and it goes up and it comes back down and it hits at the same height, then the time it took to get to the highest point is the same as the time it took to fall from the highest point. And the speed of an object at a height h above the surface of the Earth is the same on the way up and on the way down, but, well, if I take a ball and I throw it up and it comes back down, and I say I'm looking at this height h above the ground, the velocity will be the same. The difference is, the speed will be the same. The difference is that it will be moving in the opposite direction. So, but in the opposite direction. And since it's moving in the opposite direction, that means it also has a different sign. Okay? Positive, negative, or otherwise. The velocity of an object at the very top of a path, and this is an important thing to remember, the velocity at the very tippy top, in order to go moving up to moving down, the velocity at the top, which is right there, is 0. But the acceleration is still negative 9.8 meters per second squared, because otherwise it would just float. It wouldn't slow down anymore. Okay? It got to the top and it just stopped. It wouldn't go anywhere anymore. Okay. Any questions about this? Please ask me later on.